All righty, ladies and gentlemen, welcome back to our second session for today. We're going to continue with our presentations momentarily. I want to introduce the next couple of speakers. I am reading their bios from a piece of paper, so pardon me for any missteps. Dr. Taylor is a professor of mathematics, associate professor of mathematics at TSU. His degree is from University of Arkansas, and he focuses his research on abstract algebra and algebraic geometry. He's going to be teaching us about matrix calculus. We've also got Dr. Doug Harden here, who has a PhD in applied mathematics and from Georgia Institute of Technology, and he is a professor of mathematical and biomedical informatics at Vanderbilt. Both of them, I believe, are going to give us very good information, so I hope you enjoy it. I've got two things to announce. We are going to give out certificates stating that you've been here if you attend 3 sessions. The way we're doing that, if you're here, is by the sign-in sheets up at the front, so please make sure you've signed in. And if you're online, we're just going to look and see who was online. Secondly, there was another thing. Okay. Dr. Seckman is going to save me again because I've forgotten the other thing I was going to tell you. Things happen.
So there were a couple of questions during the break. So I want to make the link between what we did teach this morning and tomorrow. Okay. So what did we learn? Yeah. Okay. So we have the data matrix W, right? Give me 1 second. Those. Okay. So we have the data matrix W. And I want to go to that face example that somebody asked, that features, right? So initially we start with no features. Okay. So we construct our data matrix W. Everybody's okay with that? So if we have, let's say, 1,000 data points and each one is 5,000 dimensional, we have 5,000 by 1,000 data matrix, right? So from this one, we do PCA and maybe reduce the dimension to something reasonable, right? But still we didn't extract features. Prior to CNN, CNN stands for convolutional neural networks. We used to have regular neural networks, right? Fully connected networks, for example. You don't have to know the details. So just regular neural networks. Tomorrow you're going to learn more about CNN and so on. But before you use a regular neural network, you first take this one, do feature extraction. And then you send it to neural network. Feature extraction is important. Remember in that car example, I told you there are certain feature points. Okay? Feature extractions, there are commonly used methods. One is SIFT or frequency capstone coefficients, MFCC, for audio and for vision, for example. So that means before you send your data to a neural network, you extract features first. Prior to CNN, the best model was associated with the best feature extractor. Because if you can extract better features, your neural network is going to perform better, right? So, but now with convolutional neural networks, convolutional neural network replaces basically feature extractor. So now with convolutional neural networks, you don't have to extract features explicitly. You train a neural network that extracts the features for you. Therefore, CNN is called automatic feature extractor. You see how useful it is? Regardless of your data, this guy is going to tell you the best features, hopefully. Okay? And this one will be simple classifier for you. Tomorrow, Dr. Yuan-Kai Hu is going to explain the mathematical working of CNN. But so far what we did basically pre-processing of data that will go to what? CNN. Does it make that link now? Okay? Yeah, very good. That's all I need to explain.
I'm just here to redeem myself. I didn't forget. There were two things. The first one was, yes, we're doing certificates. The second one was, please sign in so we know you were here. I combined them both because they're both part of the same thing.
Okay, thank you very much. Thank you very much for the invitation to come and speak to this. As Chris said here, I am a mathematician by training. I'm a mathematician by profession. And I love it. But I've also got this interest in what AI, deep learning can do. And I'm particularly interested in the part of it that Dr. Sekman just talked about, this convolutional neural networks. How do you get an algorithm to train itself automatically without you having to teach it? And it's a fascinating topic. Dr. Harden and I are going to take this afternoon and talk about some of the mathematics behind how we optimize things. Because when we have a convolutional neural network and we want it to get better and better and better and better, we need to be able to measure how it's doing currently and how we need to change it in order for it to do better. And the way that we do that is we create a mathematical model, a function, which gives out a number which tells us how well this thing is doing. And we're either trying to maximize it or minimize it depending on the exact form that the model takes. So we're going to be looking at that today. I'm going to be focused on the calculus review, the calculus 1 review, basically what happens in what we call the one-dimensional case. I'm going to have a single function of a single variable, and I want to say, all right, where does it reach its maximum? Where does it reach its minimum? Dr. Harden is going to go on from there and say, okay, well then what happens when we have more than one input? What if we have a function of multiple variables, which is where a lot of the most interesting stuff happens. Now, a lot of us have seen some of this before, but I did want to get just a sense from the audience here, if you wouldn't mind indulging me for a second, to get a sense of how familiar our audience already is with just a couple of the basic words, concepts that we're going to be using here. So please, if you know what a derivative is, you're comfortable with a derivative and the sense of calculus, would you please raise your hand? Okay, so that's maybe about half the group. Okay, great. How about a gradient? Okay, all right, almost the same number. Okay, that's very, very good. We're going to talk about these things and we're going to remind you of the meanings behind them. I'm going to talk a little bit about how one computes the derivative, give some examples, but I'm not going to focus, I'm not going to spend a huge amount of time on that. I want us to more think about the meaning behind the derivative and how we can use it for optimization. So let's go ahead and get started. And there we go. There we go. All right, so source for this, source of some of the figures, some of the definitions, things here. Calculus Early Transcendentals, 9th edition by James Stewart. Although this should say Stewart, Clegg, and Watson. Apologies. James Stewart has been writing calculus texts for a long time and recently added on some co-authors. So, as I said, I'm going to be talking about single variable calculus, particularly talking about functions, some limits and continuity, and derivatives. Those first and fourth topics are really what I'm going to be spending most of the time on here. So, single variable calculus, the one-dimensional case that I mentioned, deals with functions of one variable. And these are usually given in math classes by a formula. F of x equals 1 over x squared plus 1. You give me a value of x, then 1 over x squared plus 1 gives you the output of that function. And they can be complicated. They can have trigonometric functions in there. You can have functions of variables other than x. And in math class, you usually have a formula like this. In practice, we usually don't. And so we're going to have some information about how we handle the fact that we're dealing with functions that aren't given by just a formula you can handle using pure math. A little bit of a more formal definition here. A function is just a collection of inputs and outputs, a collection of pairs x and y with the rule that each input has only one output. This is how in math we think about a function, these collections of inputs and outputs. When we have a pair, an input-output y, x, y, we write y equals f of x. This is the most familiar function notation that we have. Some terminology we have here. If we want to know all the inputs of a function, all the possible inputs you could get and get something out of it, that's the domain. The set of all outputs that you could possibly get out of the function is the range. And so a very simple, familiar example is that the area of a circle is a function of the radius. You give me a particular radius for a circle, there is one and only one area associated with that circle. And in this case, that function can be written down as a formula, a equals pi r squared. Very familiar. Functions can also be thought of, intuited in different ways. And so there are various models that are commonly used for functions. Sometimes we think of a function as just a machine where I put in an input and an output pops out. So the machine model up there. We could also think of a function as being a collection of lines, a collection of arrows that take things in the domain to things in the range over here. But the most common way that we encounter functions is by their graphs. And a graph is just the collection of all points x and y, where x is something in the domain of the function, y is the corresponding output. A function, remember that in math, a function is just a collection of points. That's all it is. A function is not a formula, it's just a collection of points. Which means that, in fact, mathematically speaking, the graph of a function is the function itself. A function and a graph, they are, in fact, the same thing. So we use a graph to understand a function because it carries all the information about it. We can read some things off of the graph, like the domain and range in this example down here. If I look at the function and I sort of project it down onto the horizontal axis, the x-axis, the set of all points in that shadow are the domain. Or if I project horizontally onto the y-axis, the set of all points that I get there, well, that's the range. Looking at the graph of a function is how we're going to start thinking about the functions, and in particular thinking about the derivatives. A couple of simple examples here. Many of us are familiar with y equals mx plus b, the equation of a line. And linear functions are, well, there's the types of things that we spent most of the morning talking about. Linear algebra, more complicated than just this, but they're built in there. But even when you're building a convolutional neural network or some other AI system out of essentially linear algebra pieces, when you combine those together a bunch, you get nonlinear functions. Nonlinear functions like, well, f of x equals x squared is one of the classic examples. And instead of the graph of it being a line, it instead forms this parabola. And in particular, one difference between the linear function and the quadratic function over here is that the quadratic function actually has a minimum value. We think about the range of this linear function, its range is actually all real numbers. All real numbers show up as some y value of a point on this line, but this parabola only goes down to a y value of 0. It's impossible to get anything lower. And so if we've got some function that we're modeling by x squared, and we want to find the minimum value of it, well, identifying where that point is really, really important to us. We do that by looking at the derivative. Now, I'm going to give essentially the intuitive definition of the derivative here first, because it's the correct way to think about it. If I look at the graph of a function, f, then at any point on that graph, I can consider the slope of the line. And I'm going to have an example here in just a second. So the derivative function f prime is the function that tells you the slope of the tangent line to the graph of the function f at the point x. At the point x comma f of x. And so here's an example to illustrate what's going on. The blue curve in this case is the function that I care about. F of x equals negative 1/2 x squared plus 1. And it forms this parabola, this downward facing parabola here. And now if I focus at the point negative 1 comma 1/2, if I were to graph this, say on a computer, and zoom in really, really closely to that point there, then the graph would look basically like a line. And if I draw the line that matches the behavior of the function as much as possible at that point, I wind up with the line y equals x plus 3/2. Because that line has slope 1, because the coefficient of x is 1, we say that the derivative of the function f, evaluated at negative 1, is 1. The slope of the tangent line to this function, when x equals negative 1, is 1. And similarly, the red line shows us the slope of the tangent line over here at 2. At 2 comma negative 1, the line that most closely matches the behavior of the graph at that point has equation y equals negative 2x plus 3 with slope negative 2, and therefore the derivative of this function at 2 is negative 2, the slope of that tangent line. So that's great. Then this tells us a lot of information about the graph. So how do we compute it? The definition that I gave was really an intuitive definition. Let's look at the technical definition. The initial problem of calculus, that really starts all of calculus, is that if I want to compute a rate of change at an instant, I wind up trying to compute a slope over a zero distance. I only know how to compute the slope of the line between 2 points as rise over run. So if I want to know the slope at a single point, what I have to do is I have to build it up and reach it by looking at the slopes of what we call the secant lines. So if I've got this function here and I look at 2 different points on the graph, P and Q right there, I can construct the line that goes through the 2 of them. That is known as the secant line, and I can certainly compute its slope. Its slope is just the difference in the y values, f of x minus f of a, divided by the difference in the x values, x minus a. Right? That gives me the slope of the secant line. Now, what happens is that I can compute if I want to know the slope of the tangent line right at P, I can compute the slope of the secant line as P goes between P and some point Q over here, but then I can imagine sliding this point Q towards P. And as I do that, I wind up getting a whole bunch of these tangent lines, but as Q moves closer and closer and closer to P, equivalently, as this point X moves closer and closer to A, the slopes of these tangent lines get closer and closer to the slope of the secant lines get closer and closer to the slope of the tangent line. Now we compute that by taking the limit. So the limit says, okay, if I plugged A into this formula, it wouldn't make any sense. It would just be 0 over 0. But I can ask, well, what does this function do? What does this expression get closer and closer to as x gets closer and closer to A? And that can be well-defined, often is well-defined. And so this gives us our formal definition for the tangent line, for the derivative. The derivative of the function at a point A is the limit, as x approaches A, of these slopes of secant lines. This is useful for a couple of reasons. First of all, it will allow us to develop formulas that let us find the derivative function, which allows us to compute the slopes of these tangent lines, without having to go through this process each time. We have formulas that we can use to handle that when we know a formula for f. This is also useful, however, when we want to know, or at least approximate, the derivative of a function when we don't know a formula. So we can imagine that we maybe have a function f that we want to study, but we don't know a formula for it. We don't have that f of x actually equals some formula in terms of x. but maybe we have some mechanism by which we can evaluate f at specific points. So if I wanted to approximate the derivative of the function at the point P, I could try taking another point Q that's very, very, very close to P. Choose an x that's almost at A and evaluate this fraction. That will give me a number that is close to the derivative, even if I don't have a formula for f. In many cases, that's what we have to work with. Now, when we do have a formula for f, though, we have some rules that let us compute the derivative function efficiently. So we've got this here, and the first thing that I have to tell you or remind you is that there are lots of different notations for the derivative. This is a small sampling of the different ways that the derivative has been defined. You go to the physicists, they use other terms beyond these ones. You talk to other people, they use different things. The derivative shows up everywhere. And so every discipline has developed its own rules for, or its own notation for it. So we're mostly going to use the prime notation here, the d over dx notation here, also called Leibniz notation, as opposed to the Newton notation over here. Look up that feud. It's fantastic. Newton and Leibniz hated each other. But one bit of notation that you'll see a lot more of when Dr. Hardin comes up is this notation here, the subscript x, to indicate taking the derivative with respect to x. So I wanted to throw that in there to see how it's going to go further. So we've got these various notations, and we can start thinking about how we actually compute derivatives. Now I'm going to go through these rules and these examples. I'm not going to belabor this point, these points, but I did want to remind us that we actually can compute these things. For instance, the derivative of a constant function is 0 everywhere because the slope of a horizontal line is 0. Wrong button. There we go. If I've got a power function like x to the first power, that has a slope of 1. It turns out that when you apply the limit formula, apply some rules to compute limits, that the derivative of the x squared function is 2x. Derivative of the x cubed function is 3x squared. And we see a pattern arising here. And in fact, for any real number n, then we have that the derivative of x to the nth power is n times x to the n minus 1. So we use that. We use that quite often, and because this rule works for any real number, it allows us to handle integer powers like this. It allows us to handle rational functions in some cases. So for instance, 1 over x can be written as x to the negative 1. All of a sudden we can use that same rule, get negative x to the negative 2 or negative 1 over x squared. We can even handle things like roots, because roots are just powers in disguise. Anything that you can write as a power, you can apply the power rule to compute its derivative. We have the natural exponential function, e to the x. E to the x is a special function which has the property that its derivative is itself. And one can almost take that as the defining property of this function. All right, so we can handle exponentials. We can handle trigonometric functions, and these are very nice too. And I do want to take a moment here to just look at this graph, though, because understanding how the graphs of the function and the derivatives are related are, of course, important. That's how I started the whole story. So if I look at the function sine x over here, I can look at its graph like this. And in particular, I want to pay close attention to the peaks and the troughs of this graph. As the function goes along, it starts at 0, it comes up, and it hits a maximum right there. And right at that maximum, we have a horizontal tangent line. A horizontal line has slope 0, and therefore its derivative function must have a value of 0 when x is pi over 2 at this peak. Similarly, when x is 3 pi over 2, the derivative must be 0, and so forth and so on with all of the other peaks and troughs. And I'm going to come back to this because remember, our whole idea here is we want to find where we get maxima or minima. We can also look and see that right here at 0, the tangent line to this function has a positive slope, and therefore the derivative must have a positive value. At pi, the derivative has a negative value because the tangent line has a negative slope. And so when you graph this out, well, that derivative function looks a whole lot like the cosine function, and it turns out that it is in fact the cosine function. The derivative of sine is indeed cosine. Derivative of cosine is, well, negative sine. If you draw it out, you'll see that you get the negative sign as well. So we can handle powers, exponentials, we can handle trigonometric functions, and we can also handle combinations of them because there's rules that tell us how to combine functions together if you know their derivatives. Take the derivatives of those functions. Constant multiples don't affect the derivative. They just come along for the ride. If I take the derivative of 5x to the 10th, that's just going to be 5 times the derivative of x to the 10th, which would be 10x to the 9th, so we get 50x to the 9th. Constant multiples are easy. Sums and differences are also easy. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. This combined with the previous fact tells us that the derivative operation is what in math we call linear, because it is compatible with both constant multiples, I mean scalar multiplication basically, and with addition and subtraction. So if I want the derivative of a sum, I just take the derivative of each piece. Now, it would be great if the rule for products and quotients were the same, but it's not. And this is where a lot of the texture to calculus comes in, to understanding derivatives. It's not just, it doesn't just respect addition, subtraction, and multiplication, and division. No, something interesting is happening here. The derivative of a product follows this rule here. If I want to know the derivative of a product, I actually need 2 terms. One where I've taken the derivative of one of the terms, and one where I've taken the derivative of the other. This is known as the Leibniz rule. Same guy. The derivative of a quotient has a more complicated formula, sort of related. Here, where the derivative of a quotient involves a combination of functions on top of a fraction and then a denominator down here. I'm not asking us to memorize these things, especially if it's been a little while since you've used them. The point I want to make is that by combining all of these rules, we can take the derivative of essentially anything that we could write down. We can take the derivative of x squared sine x. Well, if I want that derivative, well, that's a product. That's x squared times sine x. So I apply the product rule. X squared times the derivative of sine plus sine times the derivative of x squared. Now, for each of those pieces, I apply the appropriate rule. The derivative of sine is cosine. The derivative of x squared is 2x. And then because mathematicians are picky about where we put our terms, we put the 2x in front. Now, the most complicated one of these rules is the chain rule, because there's one operation that functions have that numbers don't. Numbers have addition, subtraction, multiplication, division, and powers, but functions have composition, where we are going to take one function and put another one inside it. Using the machine model from when we were first talking about functions, we could imagine a composition of functions as putting 2 functions in series. So I've got a function g, and I can put an output x. I can put an input x into this machine, get out g of x. Well, then I can immediately hook that in to the machine f, and I would get f of g of x. And this whole box right here is the function f composed with G, using this open circle notation to indicate composition. Now, what composition of functions corresponds to is applying several operations in sequence, like multiplying several matrices together in a row, or applying several layers of a neural network in sequence. And so the chain rule shows up all the time. The rule for applying the chain rule, in math we say you take the derivative of the outside times the derivative of the inside. That's our mnemonic for this. So if F is capital F here is F composed with G, like we have down here, then the derivative is given by taking the derivative of the outside function, leaving the inside the same, and then multiplying by the derivative of the inside. This is easier to see, in my opinion, if we write it down, again, using the Leibniz notation. Where if we imagine that y is a variable, which is f of u, so y depends on u, and then u is a function which depends on x. Now, if I want to know how y changes when x changes, what I need to do is I need to first ask, okay, well, how does u change when x changes? That's measured by du dx. And so then changing x a little bit, the rate at which u is changed is measured by that value. And then that u changing means that y is going to change, which means that we need to multiply by dy du. So understanding how the expression on the far left depends on the input x over here involves going through this chain, hence the chain rule. So if we can look at a simple example here, the chain rule shows up everywhere, of course. So if I've got the square root of x squared plus 1, well, I know how to take the derivative of a square root function. We saw that before. I know how to take the derivative of x squared plus 1. That's just a polynomial. Those are easy. And so I've got the polynomial as an input to this radical square root. And so I can break this up as an outside function, f of u being the square root of u, and where u is this g of x expression, which is x squared plus 1. Now, the derivative of the square root function, derivative of square root of u, is 1 over 2 times the square root of u. We saw that example earlier. I went through it quickly, but we did see that example earlier. And so this means that if I want the derivative of the big function, I need to take the derivative of the outside, 1 over 2 times the square root of u, but I need to make sure to actually plug back in the inside part, the x squared plus 1 that was there. So we get 1 over 2 square root x squared plus 1 times the derivative of the inside. And the derivative of x squared plus 1, well, that's just 2x. And so that simplifies down to here. Now, the chain rule really does break open taking the derivatives of really anything that you could write down. Any formula that you could write down can be written in the form of a composition or an addition, subtraction, multiplication, division, constant multiple, things like this. The chain rule also opens up some more advanced techniques, sometimes known, for example, implicit differentiation is something that you may be familiar with, which can be used to solve lots of problems, even ones that don't look like they can be handled by these rules. All right. So, how do we use all this? The big point there is to remind you, if you've seen this before, but also, again, to point out that we can, in fact, work with these derivatives here for any function that we have a formula of. Now, the real big applications are finding the maximum and minimum, as I mentioned earlier. So, if I've got a function here, I've got various words that I can use to describe points on the graph. For instance, on this graph that I have here, the point here at 4, 4, we describe as a local minimum. It's a minimum because it's a low point, and it's local because we are only looking at the point immediately around. We're only looking at places immediately around. Oh, whoops. immediately around here to say whether it's a minimum or not. A local minimum is just the minimum within its immediate neighborhood. We can also talk about a local maximum here. And then a point which happens to be actually the lowest point of the function across its entire domain, well, that's what we would call an absolute minimum. Or an absolute maximum would be the highest point that it reaches across its entire domain. There are various things that can happen. So, for instance, a function can have multiple absolute maxima as long as they all share the same height. They're all at the same highest level. You can have multiple absolute minimum. And so these are the points on the graph that we would like to find. Now, calculus, it turns out, is really, really good at finding local minima and finding local maxima. So we're going to talk about how we can use the derivative to find these local minima and local maxima. Determining whether or not you found an absolute maximum or minimum or a global maximum or minimum can be a very difficult question. I am going to be focused entirely on locating these local minima here. I'm going to be leaving those other questions for later speakers. So let's think about how we might identify where a local maximum or local minimum of a function is. Well, I mentioned it before when we were talking about the sine and cosine, and the trick is that at a local maximum or minimum, assuming the function is nice and smooth and you actually have tangent lines at every point, the local maxima and minima will always occur someplace where the tangent line is 0. These we call critical points, or sometimes critical numbers for C and D. And the theorem, as stated here, is the most important theorem in the in optimization from the calculus point of view. If a maximum or minimum occurs, the derivative is equal to 0. We can determine whether we have a maximum or a minimum by looking at whether the function is increasing or decreasing. That can be told to us again by the derivative. So the derivative tells us whether our function is increasing or decreasing. And it's given by the sign of the derivative. So if the derivative is positive, well, that means that the slope of the tangent line is positive. But a positive sloped line increases as you move from left to right. So if the derivative of a function is greater than 0, then the function is increasing, either at that point or on that interval. And we talk about it. Similarly, if the derivative is negative, that means the function's decreasing at that point. So what that means is that if we have a point located where we think we have or where we know that we have a critical point where the derivative is 0, like at the point B up there, one way that we can determine whether we've got a maximum or minimum is to test the derivative on either side of it. And if we did that here, and we computed the derivative here just to the left of B, we would find that the function is increasing. And if we tested the function just to the right of B, we would find that the function is decreasing. Well, if a function increases and then has a horizontal tangent line and then decreases, you must have had a maximum there. Similarly, if a function decreases, has a 0 tangent line, and then increases, well, you had a minimum right there. This is sometimes known as the first derivative test or the increasing-decreasing test. Yes, I got a little ahead of myself here. Yes, the first derivative test here. Suppose that C is a critical number. As I said, that means that the derivative is 0. And if the derivative changes from positive to negative at C, then F is a local maximum. If F changes from negative to positive at C, F is a local minimum. I got ahead of myself. I gave my spiel for this slide on the previous slide. All right, so let's look at an example. So let's suppose that we have the function g of x is x plus 2 sine x, and we want to find any local maxima or minima this function has on the interval 0 to 2 pi. Well, we start by taking the derivative. We want to know the critical points, which means we want to know where the derivative is 0. Because we know the formula for g, that means that we can compute the formula for g prime, which means that we can set it equal to 0. And if I set 1 plus 2 cosine x equal to 0, and I solve for cosine x, I find that cosine x has to equal negative 1/2. And of course, I remember my unit circle perfectly, and so I know that on the interval from 0 to 2 pi, cosine equals negative 1/2 exactly when x equals 2 pi over 3 or 4 pi over 3. Now that gives me the critical numbers. Oh, sorry. That gives me the critical numbers. And I could now go and I could test the derivative at other points. I could test the derivative at some point just to the left of 2 pi over 3, just to the right of 2 pi over 3, see whether we get positive or negative. And similarly over here. So it turns out that the function actually has a maximum, a local maximum at 2 pi over 3, a local minimum at 4 pi over 3. But we actually need something better. This is really, really good when we're talking about the one-dimensional case. For the one-dimensional case, the first derivative test, in principle, tells us everything that we need. We could get away with just that. However, it turns out this doesn't work so well as soon as we go up even one more dimension. As soon as we start talking about functions with more than one input, then the notion of increasing and decreasing starts to kind of go out the window. So we want something better. And the better thing that we have is the second derivative. Now, the second derivative is just the derivative of the derivative. You have a function, you take its derivative, that gives you a function. You take its derivative again. That's the second derivative. And so what does the second derivative tell us? Well, let's take a look at this function f here. The name that we would give to this shape is concave upward, meaning that it sort of forms a bowl shape. It looks like the sides of a bowl that's sitting, right side up so that I can hold something. If I look at what the slopes of the tangent lines are doing, then I can see that I've got a positive but small slope here. So the first derivative is positive but small here, and then the slope is increasing, so the derivative is getting larger, and then the slope gets even steeper, so the derivative gets even larger. So in this case, we can see that the derivative of f is increasing, which in other words means that the second derivative, the derivative of the derivative, is positive. So the sign of the second derivative, whether it's positive or negative, tells you whether you have a concave upward function or a concave downward function. And this can also be used to check and see whether you have a maximum or a minimum at a particular point. So here's an example of a more complicated function where we can see that we have a concave downward piece and then a concave upward piece, concave down, concave up, and so forth and so on. And the point is that the second derivative will be negative on all these concave down intervals and positive on all the concave up intervals. The points where it switches between, those are known as inflection points. They're usually really difficult to identify just on a graph. But in this case, it's very kindly labeled for us. So let's look at the second derivative test. The second derivative test is something that we can use in addition to the first derivative to quickly determine whether a point corresponds to a critical point corresponds to a local maximum or a minimum. So imagine we have this point P. We already know that its derivative is 0, so we've got a critical number there. But we also know that the second derivative is positive, meaning that the graph is concave up. In that case, if the first derivative is 0 and the second derivative is positive, then f has a local minimum right there. Similarly, if the second derivative were negative, that would mean that we'd have an upside down bowl shape. and f would have a local maximum at that point. The reason why this is preferable in the context that we're talking about this weekend is that while the first derivative test, the increasing decreasing test, can't really be generalized to higher dimensions, this absolutely can. The second derivative can be generalized to work in any number of dimensions. And so we will have tests that let us determine whether we've got a maximum or minimum value of a much more complicated function. All right, so let's take a look at another example, this time using the second derivative test. So we've got f of x is x to the fourth minus 4x cubed. So if I want to use the second derivative test, I need to know the first derivative and the second derivative. So this is just polynomial. So to take the derivative, I take the derivative of each piece. The derivative of x to the fourth is 4x cubed. Derivative of 4x cubed is 12x squared. Bring the 3 down in front, decrease the power by 1. And then the second derivative, I just apply the same power and constant multiple rules. Derivative of 4x cubed is 12x squared. Derivative of 12x squared is 24x. And I've got f prime of x and f double prime of x here. Wrong button. So if I look at 3, if I look at the input x equals 3, then f prime of 3, well, that equals 0. I plug 3 into this function, I get 0 out of it. And if I plug 3 into the second derivative, I get 12 times 3, 36 times 3 minus 2 is 1, so I get 36 out of it. I really don't care about what number I get out of it. I just care, is it positive or negative? In this case, we have that the second derivative of 3 is positive. So that means that right at 3, the function has a horizontal tangent line and is concave up, with our conclusion being that the function has a local minimum at 3. The value of it we find just by plugging it into the original function, and so we can say that f of 3 equals negative 27 is a local minimum of this function. As a quick aside, continuation, there's another number where the derivative is 0. There's another critical number that we could determine from this function. 0. Right. So if I plug 0 into f prime, I get f prime of 0 is 0. So we certainly have a critical number at 0. And then f double prime of 0 is also 0. That's inconclusive. That's inconclusive. A second derivative of 0 could correspond to a local minimum. It could correspond to a local maximum. And it doesn't even need to correspond to an inflection point. If it's concave up, hits 0, but then is concave up again afterwards. Unfortunately, getting a result of 0 is inconclusive here. So the second derivative test, while it works really, really well, there are still places where it doesn't give us all the information we need. In this context, in the context of a one-dimensional function, we would just go back to use the first derivative test, the increasing, decreasing test. That takes care of it for us. All right. So I want to end my portion of this afternoon by thinking about how we can use these ideas of looking at derivatives and second derivatives to come up with some sort of strategy. How would we actually find the minimum value of a function? And I especially want to think about the situation where we don't have the formula for the function, where we can't just do all the algebra that we just did, but instead we have some other source of information. We have some oracle, this is sometimes called, where we can just ask the oracle, what's the value of the function at this point? And it'll give us that number back, but won't give us any additional information. So suppose that we want to find a minimum of f of x near some starting point x0. I'm going to focus on minimum here because, of course, the maximum situation is almost identical. Now, suppose that you know that the derivative of the function at x0 is negative. That means that the function is decreasing at or near x0, which means that if I were to increase my input a little bit, my function values would go down. I don't know what my function looks like exactly, but I know that right near x0, it looks something like this. It's got a negative slope, which means that if I want to find a smaller point on the graph, if I want to find a lower point on the graph, I need to move a little bit that way. So near x0, f of x is decreasing, so increasing x will decrease the actual value of the function. So we could try to increase x0 slightly to a new input, x1, and check again. And we can ask the oracle again, is my function increasing or decreasing at this point? And it's like, well, maybe it's still decreasing. Well, if so, we could go another little step along and then, try to find a place where the derivative is actually equal to 0. If the derivative had been positive instead, well, then we would just move the other direction. If the derivative of the function is positive, that means the function is increasing at this point, which means if we want to find the minimum value of the function, we need to go to the left. So I wanted to show you a bit of pseudocode. As I said, I'm not a computer scientist, I'm a mathematician, but I can write pseudocode, which means I can program in Python. And so I want to find a value x where f of x has a minimum. Now I say just minimum there. In fact, this algorithm will only guarantee that I've found some local minimum here. But we start with the following. We have an oracle for the sign of the derivative, and I should say I also want to know a sign for the second derivative as well, so that at the end I can run my second derivative test. I have a starting guess. I have a guess as to where the minimum might be. And then I have some step size that I've determined here. And I have to specify what precision I want, how close how much error I'm going to allow myself in my answer. All right, so I start with just let x be my starting point. And then if the derivative is positive, that means that the function is increasing at x0. And so I'm going to make my delta x. My delta x is my actual step that I'm going to be making in the algorithm. I'm going to make that negative so that I'm moving to the left. Otherwise, if the function is decreasing, I'm just going to let my step size be my starting step size, positive, going to the right. And then we're going to go in a loop. We're going to determine the sign of f prime of x. Now, if we have gotten to a critical point where the derivative is 0, or our step size is below our desired precision, then we stop. We can return the x that we found. And then otherwise, we can choose our step size appropriately. I apologize. When I wrote this up, I realized now I was slightly redundant between what I did up here and what I did down here. It's the same logic here. If the derivative is negative, you want to increase your input. If the derivative is positive, you want to decrease your input. All right, so you do that, and then so long as that same relationship holds, so long as your derivative function is indicates you're going in the right direction, you want to just keep setting x to be x plus delta x. Just keep stepping in that direction until your oracle for the derivative says, oh, you've gone too far. The function started, it switched its direction. Well then, what can we do? We can cut our step size in half, turn around. And we can step back using a smaller step size until we've passed our minimum again. And then we say, okay, let's turn around, cut down our step size again. And we can just, in principle, keep going back and forth like this, where the idea is that at every point we're following the derivative. We're letting the derivative tell us which direction we should go. If the derivative is negative, we keep increasing x. If the derivative is positive, we go the other direction. This is a one-dimensional version of a technique that Dr. Hardin's going to talk about called gradient descent. It is not a term that's typically used in the one-dimensional case. We don't tend to use the term gradient here. Although interestingly, in Europe, they often do use the term gradient just to mean what we mean derivative there. So it's a little bit more consistent. So the point is that this is a one-dimensional example of that. And the idea, you follow the derivative. Yes, go ahead. I'm sorry. I'm sorry. An odd function? Uh-huh.
If that is a given problem, like if it's a positive, then we don't do that x is equal to x plus a.
Oh, we do. In that case, del x will be negative, if I'm understanding you correctly. So if the derivative is negative, then we want del x to be positive. So as long as that's true, then we keep increasing x. Right. Yeah, because if the derivative is negative, that means that we want to make x, we want to increase x. We want to keep adding positive values to x. And if the derivative is negative, we want to be decreasing. I'm sorry, if the derivative is positive, we want to be decreasing x. All right. Are there any questions? Yes, go ahead. Any global minimum is automatically a local minimum. Because if you're a global minimum, that means that you are the smallest output of the function across all possible inputs. A local minimum just means that you are the smallest output within a small area. So if you're the shortest person in the world, you're certainly the shortest person in this room. And so every global minimum is a local minimum. Absent some different authors have different technicalities about what happens at the very end points of an interval. I'm not interested in. I'm only interested in these minima that happen, somewhere in the middle of the domain. Does that answer your question? Other questions? For this algorithm, if the first derivative is 0 right from the bat, we got to do something else. Because if we happen to just guess right off the bat that the first derivative is a number where the first derivative is 0, that means that we got really, really lucky or possibly unlucky, and we found a critical number right on our first guess. Now, that might be a local minimum, and it might be a local maximum, and it might be neither, actually. So for that, you'd need to do something else. You could use the second derivative test immediately and see. You could also, assuming you have access to it, to something that can tell you the values of the function, you could also just start looking at the values of the function nearby your initial guess, which would sort of be, that'd be going back to sort of the first derivative test, things that we mentioned here, where you see, well, okay, is the derivative going from positive to negative? Well, that means that we have a maximum. But to do that, you would test the derivatives on either side of whatever point you started. Mm-hmm. Yep. Absolutely. Let me go there. So here's a really good example. So this is the cosine function. Yes, you can absolutely have multiple absolute minima, or multiple global minima, or multiple global maxima. They just all have to be the same. They just all have to be the same level. So you could have two shortest people in the world, as long as they were the same height. In this case, if we applied the sort of algorithm that I was looking at here, one of the hardest things to do is to determine what your initial step size should be. because you want to be able to move far enough that you get to your minimum in a reasonable amount of time, but you don't want to overshoot it. So for instance, if I am trying to locate this minimum right here, and I start off with this number as a guess, but my first step size shoots me all the way over here, well, then I'm probably going to find this critical point, or possibly this one down here, rather than this one over here. So this is a problem that needs to be solved in practice. These are practical problems that need to be handled in whatever implementation and whatever the specific algorithm is that you're looking at. No algorithm is going to be perfect in terms of being able to avoid missing minima, things like this. And I'm sorry, did I completely answer your question? Sorry. Yeah. Uh-huh. So depending on what algorithm you're doing, if you use an algorithm like the one that I looked at down here, you would get to one of these and you would stop. So most algorithms you have for finding minimal values will stop once they find a minimal value. And so the algorithm will not give you all of the minima. The algorithm is to find a single minimum, and then the question remains, are there others? Right. So that's, yeah, we won't, especially if we don't know the full shape of the function, which is the situation where we would use an algorithm like that. And yes, we will be able to find one point, but knowing that point won't tell us about the shape of the rest of the graph. We generally don't know ahead of time what that minimum is. But we will find one, and then you may very well ask, are there others? So you might try running this algorithm starting from a lot of different starting points to find a lot of different local minima, as an example of how you might get around this. Yes, please.
Think about like, this is what I got, this is what I expected. Let's look at the difference. That's the loss function of error. And you're trying to minimize that error every iteration, right? So it depends. So always you're going to find a local minimum. And if that local minimum is acceptable for you, you stop. But if you say, hey, this error is still too much, then you're going to keep going until you find a local minimum which is acceptable. It is impossible to find, it is impossible to be sure that something is global unless you check everything, right? But you don't have to know that. Add a function, minimize it, see if it's acceptably minimal for you. If not, continue to get the next local minimum. And then finally, hey, this error is acceptable for you.
Designer or the problem solver's choice?
Well, typically, either you say, hey, I'm going to go 1,000 iteration, and if that 1,000 iteration, if nothing is changing in the 10 consecutive iteration, I will stop. That error is not decreasing more, so maybe I should stop. Or during that 1,000 iteration, your error is 0.001, which is in the range, you can stop it. Or you can go all the way 1,000, hey, my computational power is this much, so I will stop whatever that is.
All right, thank you very much.